Math 1314, Tyler Junior College, Section 4.4, Exponential and Logarithmic Equations. Exponential equations like bases. In this series of videos, we're going to solve, well, exponential and logarithmic equations. Solving equations is one of the big ideas in algebra. Here's an equation involving an unknown value. Figure out what the unknown value is. For those of you going into calculus, you will be solving lots of equations and lots of different types of equations, including exponential and logarithmic. So just a heads up for those of you going beyond this class. Now for everybody in this class, I still want you to be able to solve exponential and logarithmic equations. Just letting those who are going beyond into calculus know that it's not going away. So how are we going to solve exponential equations with like bases? Well, we're going to build a strategy based on something that we've already taken advantage of before. The fact that exponential functions are one-to-one. Recall that the function f of x equals b to the x, as long as b is positive but not equal to 1, is a one-to-one function. This means, ideally it means the only way to get equal outputs is if you have equal inputs. Symbolically, you could say that f of, we'll say capital M, equals f of capital N implies that m equals n. In other words, the only way two things can come out the same is if they went in the same. Specifically, if we apply this function to both of these inputs, we're saying that b to the m equals b to the n implies m equals n. Almost as if the bases just cancel and you equate the exponents. That's one strategy we're going to use in some exponential equations. If we can get them in this form, same base on both sides with different looking exponents, then we can just equate the exponents and go from there. Let's write down our move over here. B to the m equals b to the n implies m equals n. So what type of equations can we solve using this strategy that if we see something that looks like this, we can rewrite it like this? I'll have a couple of examples in mind. For example, the first example we're going to solve is 2 to the 7x minus 1 equals 32. Let's go ahead and set up the second example as well. Solve, let's see. How crazy do I want to make this? You know what? I had a simple example in mind for the second one, but why hold back? Why hold back? Let's solve, come on, I know you're in here somewhere. Really, you're not giving me much to work with here. Well, fiddlesticks. I thought I'd find one that did something nifty, but I'll just make one up. Solve, we'll say 27 to the 2x minus 1 equals 9 to the x plus 4. By the way, I have no clue what the solution to either of these are, but it doesn't matter. As long as you have a plan of attack, you can find the solution. So how does this plan of attack go? We'll make both sides powers of the same base and then equate the exponents. Let's look at the first one. 2 to the 7x minus 1 equals 32. The base on the left is currently 2, but the base on the right is currently 32, meaning that the bases don't match. Our strategy requires that we have matching bases, so our first move is to try to get matching bases. Try to get matching bases. Can we rewrite one number as a power of the other? Yes. We can rewrite 32 as a power of 2. You may recall from previous videos that 32 is 2 to the 5th power. That means that we can rewrite the right side of the equation as 2 to the 5th power. Now the right side is a power of 2. It's base 2. And the left side was also base 2 to begin with, 2 to the 7x minus 1. And at this point, our equation now has the proper structure to take advantage of this property. If we have two powers of the same base equal to each other, we have two powers of the same base equal to each other. This implies that we can just set the exponents equal to each other. In other words, at this point, we can equate exponents. It's almost as if the twos cancel. I guess you could argue that they do. But if we equate the exponents, we get 7x minus 1 is equal to 5. That's pretty easy to solve. Add 1 to both sides to get 7x equals 6. Divide both sides by 7 to get x equals 6 sevenths. If we did everything correctly, every solution should be a solution. We did no move that could bring in extraneous solutions. So 6 sevenths is it. And if you wanted to check it, you could. But it's a fraction. Yeah, so putting the fraction here isn't as bad as it seems, because the first thing that happens is it gets multiplied by 7. And what happens when the 7 hits the 6 sevenths? 7's cancel. 7 times 6 sevenths is 6. 6 minus 1 is 5. And of course, 2 to the 5th power is 32. Bingo! But it's not always, it's not always sunshine and lollipops. On this next example, we're going to solve 27 to the 2x minus 1 power equals 9 to the x plus 4 power. But this one has a glitch. In the previous example, we got matching bases by rewriting one base as a power of the other. We rewrote 32 as a power of 2. In this case, good luck with that. Could we rewrite 27 as a power of 9? Well, 9 to the first power is 9, so 1 is too low, but 9 to the second power is 81. 2 is too high. If I'm going to rewrite 27 as a power of 9, that power is somewhere between 1 and 2. Don't really want to go there. But nobody said I only had to rewrite one base. I could possibly rewrite both. If one base is the power of the other, great, take advantage of that. If it's not, then try to rewrite both bases as powers of a smaller base. So now we're going to try to get a new base on both sides. Try to get a new matching base on both sides. And it's usually not that hard to look for a good candidate. For example, I want to rewrite 9 as the power of something. Well, 9 is 3 to the second power. So maybe we should use base 3. Well, as already stated, we know that 9 is 3 to the second power. But what about 27? At this point, you should know that 27 is 3 to the third power. But if you didn't, you could divide it by 3 and then figure that out. So let's rewrite both sides. This one's a little different though. It's a little different in that each base that I'm going to rewrite already has a power on it. Up here, the base that I rewrote did not have a power on it. These do. Why does this matter? Well, let's take the 27 and rewrite it as 3 to the third power. That 27 already had an exponent on it of 2x minus 1. And let's take the 9 and rewrite it as 3 to the second power. But the 9 already had an exponent on it of x plus 4. So why is this important? Because on both sides, I just set up the power raised to a power. And we have an exponent rule that says how to deal with that. Anytime you have a power raised to a power, the powers get multiplied. Be careful. Technically speaking, it's not time to pull off this move. I still have a base of 27 and a base of 9 over here. I'd like them to be both explicitly base 3. How do you fix that? Just multiply the powers. In this case, multiplication invokes the distributive property not once but twice. If we multiply these powers, we distribute the 3 across the 2x minus 1. 3 times 2x is 6x, minus 3 times 1 is 3. On the other side, we distribute the 2 across the x plus 4. 2 times x is 2x, 2 times plus 4 is plus 8. And now both sides are explicitly powers of 3. Both sides are base 3. And now that both sides are base 3, we can equate exponents. What I was looking for in my list of problems is a situation where when we get to this point and put the exponents equal to each other, we had a quadratic equation. I didn't find one. I didn't want to take time to make one that behaved, but it could be a quadratic equation. In fact, at this point, it could be any other type of equation that we already know how to solve. If you have a really sadistic professor, they will embed one weird type of equation inside of another, such as an absolute value or something that's a quadratic in form. But this one's just a linear one. Let's solve it. Too many x's. Let's get rid of the lesser x. Subtract 2x from both sides. We get 4x minus 3 is equal to 8. And let's finish this. Add 3 to both sides. This becomes an 11. Then divide by 4. X is 11/4. That doesn't sound right. That does not sound right at all. Oh, never mind. We could check it. It'd be a little tricky to check because the exponents would end up being rational numbers, but it wouldn't be impossible. I challenge you to try to check it. So to summarize, some exponential equations we can solve by getting like bases, meaning that we rewrite one or both sides possibly to expose the same base. In this case, the base was 2, one of them already was. In this case, the base was 3 because neither original base was a power of the other, but they were both powers of 3. Once you get equal bases, then you just equate the exponents and finish solving. This does raise a big question though. What if we can't get like bases? The truth is, you always can, even if you don't think you can. So the real question is, what if you can't do it conveniently? For example, 3 to the x power equals 14. What base are you going to use there? Well, 14 is not a power of any number less than it, so I can't rewrite it as 3 to a power, much less anything else to a power. So how can we solve an exponential equation when we can't get like bases? If you've been watching the series of videos in order, then in the previous series of videos, you might recognize that 3 to the x equals 14 power. Go back to video 4.3.7, and you may recall that, wait a minute, we saw something like that and we did something to solve it. So did I accidentally sneak in a preview of something you're about to see? No, I would never do that.